Morning everyone. My name is Ashok. I am studying BTech second year. My roll number is 24BQ5A0404. Now I am going to tell about modulation and especially amplitude modulation. Now let us start with basic definition of modulation. Modulation is the process of changing amplitude, carrier frequency or phase of the carrier signal in accordance with instantaneous amplitude of message signal. It can enable the information to transmit over long distance through various medium. Now let us see the key elements in modulation. First of all, the carrier. The carrier is a high frequency signal which is used as base of the modulation, and the second one is message signal or modulating signal, the actual information or data which carries this is a message signal. And the modulating signal, after combining message signal and modulating signal, it is called as modulated signal, which carries information over long distance. Now let us see amplitude modulation. Its definition is the process of changing amplitude of the carrier signal in accordance with the instantaneous amplitude of message signal, keeping phase and frequency constant. Now let us see the time domain and frequency domain representation of amplitude modulation. Here these are time domain and frequency domain expressions of amplitude modulation. First we consider a message signal m of t, which is am cos 2 pi fct fmt, and consider the carrier signal also, which is ac cos 2 pi fct, where ac is amplitude of carrier and fc is frequency of the carrier signal. Here am is amplitude of message signal and fm is frequency of message signal. Now let us consider the modulating signal, which is message signal frequency is far less than carrier frequency, which is near to frequency range of message signal is 300 Hz to 3 kHz, and the frequency range of carrier frequency is 500 kHz to 3 MHz approximately. Now let us consider S of t as the amplitude modulated signal. Its equation is 1 plus Ka into m of t into c of t. Let us substitute the values of m of t and c of t in this equation. After we substitute, we get am cos 2 pi fmt instead of m of t and ac cos 2 pi fct instead of c of t. Let the Ka is amplitude sensitivity and the Ka into am is it is a modulation index. Let denote with this with a new value. After so after putting the Ka into am as nu, where nu is modulation index, Ka is amplitude sensitivity. Here the Ka, it controls the depth of the modulation index of amplitude modulated signal. Now let us multiply the cos 2 pi fct term inside. After we multiplying these, we get AC cos 2 pi fct plus AC nu cos 2 pi fct into 2 pi fmt. By using this formula, we can rewrite the cos fct and cos 2 pi fmt as cos fm plus fct by 2 and plus cos 2 pi fc minus fm by 2. So this is the final expression of our amplitude modulated signal. It has three parts. One is AC cos 2 pi fct, which is carrier signal, and AC nu by 2 cos 2 pi fc minus fm, which is lower sideband signal, and AC nu by 2 cos 2 pi fc plus fm, which is upper sideband. We have finally carrier, lower sideband, upper sideband in our amplitude modulated signal. If we apply the Fourier transform to our time domain amplitude signal, it will be this expression as the formula we known as. When we apply Fourier transform to cos 2 pi fct, then it will be del of f minus fc plus del of f plus fc. We can apply the Fourier transform to our amplitude modulated signal, then finally it will become AC by 2 del of f minus fc plus del of f plus fc plus AC by 4 del of f minus of fc minus fm plus del of f plus fc plus fc minus fm plus AC nu by 4 del of f minus of fc plus fm plus del of f plus fc plus fm. Here these are the diagrammatic representation of in time domain and frequency domain, which the first signal is message signal, and the second signal is carrier signal, the third signal is amplitude modulated signal. Here this is the form of amplitude modulation, and let us see in frequency domain. This is m of t, m of f, which is Fourier transform of m of t, which is a low frequency signal, and this one it is carrier frequency signal, which has a high frequency compared to message signal, and the final one is amplitude modulated signal in frequency domain. Here we have three components. One is carrier frequency component fc, and the second one is fc plus fm. This is upper sideband frequency component, and third one is lower sideband, which is fc minus fm. In these, the carrier does not contain any information, and the upper and lower side bands carrier information, which is message signal. Now let us see the generation techniques of amplitude modulation. We have two types of generation techniques. They are square law modulator and switching modulator. Let's first see the square law modulator. The square law modulator consists consists a square law device with band pass filter. The diagram which is shown as in figure, it consists of message signal and carrier signal, square law device and band pass filter. First, the message signal and carrier signal are combined using a summizer and is applied as input to the square law device, which is represented as V1, and the output of the square law modulator is represented as V2, and then it is passed to band pass filter, which allows only the specific frequencies, which means it allows the amplitude modulated signal frequencies as we conveys that information passes. Now let us see the derivation part of square law modulator. So this is the output of square law device, which is equal to which is represented as V2 and is equal to V1 A1 plus A2 V1 square plus A3 V1 cube plus and so on, where V1 which is gets after combining the output, the message signal and carrier signal, which is as shown in m of t plus ac cos 2 pi f c t. For simplification, let us consider only the first two parts in V2. So V2 equal to A1 V1 plus V1 square A2 V1 square. Let us substitute the V1 value in V2 as shown in this expression and expand the m of t plus ac cos 2 pi f c t whole square with a plus b whole square formula a square plus b square plus 2ab. After expansion, we get m square plus ac square cos 2 pi f c t plus 2 pi fmt, and the output is the V2 is the output of square law device, which is applied as input to the band pass filter. Response of band pass filter is shown below. It allows only these frequencies only, where it allows fc minus fm to fc plus fm frequency components only. So thus we obtain the modulated signal by using square law device. So this is the final expression of our signal. Here this is the final expression of our required amplitude modulated signal. S of t equal to A1 AC cos 2 pi FCT plus A2 2 AC M of t cos 2 pi FCT. Let us common these terms. A1 AC common, we get A1 AC 1 plus 2 A2 by A1 M of t cos 2 by FCT. Let us assume these A1 and AC as AC dash and 2AC to 2A2 by A1 as Ka, where Ka is amplitude sensitivity. Here this is the our required signal AC dash into 1 plus AM M of t cos 2 by FCT. Now let us see the second generation type of amplitude modulation, that is switching modulator. The switching modulator is basically a diode and a band pass filter as shown in the screen. It consists of message signal, carrier signal and a summizer and a diode element, which is switching element, and a band pass filter. Here the message signal and carrier signal are combined, then applied to switching element is represented as V1, and the diode acts on for positive half cycle and off for negative half cycle, and the output is represented as V2 after getting V2, the V2 is applied to a bandpass filter, then it allows only required frequency components only. Now let us see the mathematical representation and derivation also. Here V2 is the output of the switching element is equal to V1 into X of t, where X of t can be shown in the diagrammatic form, where it is the diode characteristics. It have on and off cycles. When here it can be represented in the Fourier series form, which is equal to X of t equal to half 1 by 2 plus 2 by pi sigma n equal to 1 to infinity minus 1 whole power n minus 1 by 2n minus 1 cos 2 pi of ct 2n minus 1. Let us, we know the v1 of t equal to combination of message signal and carrier signal. Let's substitute the x of t and v1 of t in the above term v2. We get v2 equal to m of t plus ac cos 2 pi of ct and the half plus 2 by pi sigma n equal to minus infinity to infinity minus 1 whole power n minus 1 by 2 n minus 1 cos 2 pi of ct 2n minus 1. Let us consider the in this form two components only, which is if n equal to 1, then it will become cos 2 pi of ct. If n equal to 2, then it will become minus 1 by 3 cos 2 pi 6 pi of ct, and multiply this term with inside this term, we get this expression. First we multiply the m of t term with half, we get m of t by 2, and we multiply m of t with the second term, we get 2 by pi m of t cos 2 pi of ct minus 2 m of t by 3 pi 3 6 pi f ct. And let us multiply the second term also with half, we get ac by 2 cos 2 pi of ct, and multiply with the second term, we get 2ac by 2 ac by pi cos square pi f ct minus 2 ac by 3 pi 3 cos 2 pi of ct cos 6 pi of ct. When the signal is passed to a band pass filter, it will allows a particular range of frequencies, which is fc minus fm to fc plus fm, including fc also. Then finally we get the modulated signal as 2 pi by m of t cos 2 pi of ct plus ac by 2 cos 2 pi of ct. Let us common the term ac by 2 cos 2 pi of ct, we will get ac by 2 1 plus 4 by pi ac m of t cos 2 pi of ct. Then finally assume ac by 2 as ac dash and 4 by pi ac as ka dash, which is amplitude sensitivity, which controls the depth of the modulation. The final expression will become s of t equal to ac dash plus 1 plus ka dash m of t cos 2 pi of ct. Thank you.